Hello and welcome to this IChemE Global Awards webinar. My name is Matt Stalker and I will be your host for today's presentations. The IChemE Global Awards celebrate chemical, process and biochemical engineering excellence and are widely recognised as the world's most prestigious chemical engineering awards. Today we'll be announcing the winner of the IChemE 2020 Oil and Gas Award, sponsored by the Chemical Engineer. This award recognises the best project, process or product to demonstrate chemical engineering excellence in the oil and gas sector. Here are our finalists. Hybrid Gasification, Hydrox Holdings, a joint entry from the Norwegian University of Science and Technology, North Carolina State University and Sintef Industry. Another joint entry and winner of the IChemE Malaysia Oil and Gas Award, Petronas Research, Deakin University and the University of Adelaide. Saudi Aramco, Expect Arc, and three more entries, all from Saudi Aramco. All of our finalists have been invited to join us today and give a short presentation on their work. Subject to time, we'll be inviting you to ask questions. You can ask your questions using the questions box on the GoToWebinar portal. It's now time to welcome our first finalist. Please welcome from Hybrid Gasification, Abdullah Malik.
Hello, everyone. Can anybody hear me? Hello.
Yes, we can hear you. We can hear you and we can see your screen. You just need to put it into presenter view.
Yeah, definitely. Yes. I don't know how many in the audience as well. I can't see any number there. 39 attendees. Okay, so 39 of you guys are listening to me. Yes, my name is Abdullah Malik and I'm going to present to you my 2020 IChemE Global submission on solar powered 1 ton per day advanced unit for harvesting base oil from used lubes. My presentation, I'm not too sure how long I can take. Can I be advised on that? How long I can take on the presentation?
You have approximately 10 minutes.
10 minutes. Okay, thank you very much. I wasn't too sure. But my presentation consists of 9 slides, almost 8 slides on my previous submission in 2015, which was shortlisted. I will run through quickly just to put some perspective to where we went to the next stage of this 2020 submission, and it's been I'm happy that it's also been shortlisted for the presentation. And then I will go to some global demand for base oil, lube oil, and EU perspective on that, and in the end some conclusions. The used lube oil processing facility, first one was built, 100 ton per day capacity was built in Saudi Arabia to produce Group 1 heavy base oil. It was a vacuum distillation facility. It actually used structure packing for separation of consistent quality product. Actually, the interesting and the novel part of that was that rather than using a conventional wide thin film evaporator to treat the residue, a thin film, non-mechanical thin film device was fitted in the flash column, for which patent has been filed. So I'll take you through the I'll explain a little bit on what is non-mechanical intensified thin film evaporator. It is a device fitted on the bottom of a flash column, and so that helps to recover the remaining part of the base oil when the heated base oils enters into the flash column. And amazingly, we were able to achieve more than 80% of recovery without fitting the mechanical wipe thin film evaporator the conventional approach normally do. And we are all familiar, being process engineer working in oil and gas sector, that the problems with mechanical thin film evaporators are always mechanical seal problems. The challenge was when this was proposed by me that that we have this was the very inexpensive and practical solution. So client wasn't ready to go for this unproven but very inexpensive practical solution. So we had to do some testing, convincing the designer to of the plant. In order to convince the designer of the plant, we run a cold testing to establish the optimum flow rate for consistent quality of thin film. For that, obviously, we needed to add an additional length on the increase the length of the flash column, and for so in order when we did that, we had to elevate the peripheral equipment to accommodate the increased flash column height. So after a few iterative process discussion with the client, we got the go ahead, and we installed that, and in fact that eliminated. It performed very well, better than the thin film evaporator, no downtime, and shutdowns were seen. The plant, which are typical to the white thin film evaporator, and we saved on the additional vessel network fitting and all that. We saved on the plant downtime, and therefore we built the plant much cheaper than without this additional system, which includes pipe thin film evaporator. This is a typical 3D view of the 10 tons per day used lube oil facility, which was installed in Saudi Arabia. This is the pictures of the cooling system and the products tank form. The distillation column on the left side of the screen. If I you can see the residue, the spent lube oil converted into heavy base oil and light base oil. Now I come to my current submission, which is 1 ton per day mobile unit for the recovery of base oil from used lube. The idea was that one could run it with solar powered energy, maybe for 6 to 8 hours, unless you want to run it for 24 hours, depending on the economics where it's installed. So it has also got this non-mechanical intensified thin film evaporator fitted in it. The objective, some of the objectives here were to improve the recovery and quality of product by avoiding adulteration from random different types of oils when it's taken to the centralized facility. Improved environmental benefit by avoiding the use of fossil derived energy. And last but not least, objective was the improved environmental benefit by avoiding unnecessary transportation to and from centralized facility. There were a few challenges in building a small unit. One of the challenges was from 100 tons per day plant to downscale it to 1 ton per day. And you can imagine the process engineers and a lot of process engineering challenges were there. The recovery we could achieve was 85%, and heating requirement was met by electrical coil immersed in thermal oil. Use of solar power electricity offers enhanced negative carbon footprint. Also, that gave the benefit of sustainability, such as on-site recycling of base oil offers much lower cost than transporting to centralized facility, helps not in my backyard, NIMBY community demand, improved income for local community. Process safety wise, there were a few things which we needed to look into. The process plant operates at full vacuum and all columns had pressure relief valves installed. All control valves were positioned ergonomically for safe operation. Thermal oil circuit have been installed with flame arrestor in case fumes released catch fire. Exhaust gases post vacuum pump are released via water seal to an enclosed flare system maintained at 850 centigrade. There are some sketches of here's a 3D sketch of that small facility, 1 ton per day, with P&ID. And here on the left side of this short screen, there is this small, we built this small one is being carried once from the fabrication facility to where it was going to be installed and operated. And you can see in the middle of the picture, in the background, the same demo facility in operation with base oil recovered, pictures of in the tubes, and a control panel is shown on the right side. Summary of this is that 1 ton per day compact unit has been installed. It achieved 85% recovery. Benefits of on-site recycling will come in of base oil, and it obviously resolves in the effect we talked about quickly, and the complete processing unit easily fits in space of 40-feet container. Those of you want to have some feeling of the finished lubricant markets of the order of 40 to 50 million tons per annum globally. Global demand, almost Europe and America and Asia Pacific, they all share equal number of percentage of demand. Pakistan and India, almost 1.7 million tons of market. Global review market by sector, almost 50% in consumer, commercial and consumer sector, which can be tapped on if this process is taken forward. There's an EU perspective I've added in my presentation. Out of 6 million tons sold annually, only 2 million tons are collected. Almost 1 million tons are re-refined. Plants using hydrogenation or solvent extraction produces virgin quality oil. And a report by Fahrenbach confirms that recycling uses less energy than virgin produced from crude oil. So, an EU framework directive insists that preference for refining over fuel use. So, we should really stop using as a fuel. So, and use oil to be collected separately. Benefits to the oil sector, oil refining sector for this particular technology. Refining offers small negative good carbon footprint compared with the produced from crude oil route. Keeps lube oil in productive use and delivers improved oil security. Non-mechanical thin film evaporation can be applied in several other areas of refining. Immediate application is for recycling base oil in poorer countries where there is no need for group 2 oils, where the old cars are there and all that. So, but hydrogenation stage can be added to obtain group 2 base oil. Potential use to clean scrubber effluent contaminants, and also in the biodiesel, on the biodiesel plant for ethanol recovery. There are several more applications for this non-thin film evaporator within the petrochemical sector and refining sector. I can go to guys. There's an API perspective on used oil re-refining. I've got a couple of slides left where Bachelder confirmed that hydrotreated oils can meet API performance, provided that the oil meets API performance criteria. The source of base oil is not an issue, and one could get API certification for this type of plant. My last slide is just employing the 1 ton per day smart base oil recycling system has many economical and environmental benefits. The application of non-mechanical intensified thin film evaporation device is a leap forward in the reduction of processing costs and will replace conventional expensive evaporation technologies currently in use. So this was it for me today. And any questions? I haven't seen any question yet. I don't know. How would I get it? But I could be contacted. Any question later on, and I can send my presentation as well if IChemE requires me to do that.
Okay, thank you very much, Abdullah. So we will pause for questions. And if you do have a question, please type it into the questions box on the GoToWebinar portal. We have one already. So as this is a candidate for a global award, I have a particularly global question. What is the potential for deploying this technology to the world's remote archipelagos, easy for me to say, which have difficulties in disposing of waste oils that so often risk polluting their seas?
Yeah, there is a huge demand. It could be applied on islands, the remote areas where it's very expensive to dispose of and maintain the supply as well. So a small unit like this can help recycle the lube oil and bring keep the environment clean.
Okay, thank you very much, Abdullah. We need to move on. So thank you for your presentation. It's now time for our next finalist. Representing Hydrox Holdings, please welcome Malcolm Gillespie. Malcolm, we can't hear you if you have started talking. We can't hear you yet. You may just need to unmute and mute your presentation. No, we can't hear you still, Malcolm, I'm afraid. No, still nothing, Malcolm, I'm afraid. I'll ask my colleague Gareth to step in and see if there's any technical suggestions he can offer.
All right, thank you. Can you hear me now, perhaps?
We can, yes, loud and clear.
Fantastic. Okay, all right. Sorry, I did a couple of things on my side and I got it working again. All right, let me get straight to it then. All right, so my name is Malcolm Gillespie. I represent Hydrox Holdings and I'm the senior process engineer on the side over here. I was waiting to go to the next slide so I can start. There we are. So who are we? So Hydrox Holdings is a small research and development company located here in South Africa. But more than that, we want to position ourselves as a hydrogen solutions provider, specifically here in South Africa. Position ourselves as an OEM manufacturer of electrolyzers here. So in terms of our core activities, of our research and development is our technology that we've coined the term DEFT. It stands for Divergent Electrode Flow Through, and I'll give you a little bit of a breakdown a little bit later on in my presentation what that technology encompasses. Likewise, here locally in South Africa, what our drive is currently in terms of positioning ourselves as a commercial fabricator is we've gotten considerable interest locally in terms of a OEM solutions provider for hydrogen here in South Africa, and hence we are concurrently working on our advanced alkaline electrolysis technology as well. So that's just a brief introduction of the two technologies that we are busy championing as part of our technology. So what is the challenge when it comes to electrolytic hydrogen? So currently, around 95% of your hydrogen produced globally is from fossil fuel sources. So, for example, steam methane reforming. A small amount, 5% of the hydrogen produced is only produced from electrolytic hydrogen, and an even smaller percentage of that is green hydrogen. So what is the need for electrolysis to become successful? In order for that to happen, electrolytic hydrogen needs to become more accessible and, more importantly, more affordable. And for that to happen, you need electrolyzers to become inexpensive, reliable, compact, and to some extent they need to have an operational flexibility. And taking all this into consideration will do wonders for the CapEx, the OpEx of these systems, as well as for their overall efficiency and reliability. So those are the core issues that we're trying to tackle as a small organization located here. Moving on to the next slide, just waiting for it to change. There we are. So what are the current challenges in industry? So what you'd find is within industry where you find efficient electrolyzers, they often do come in at quite a high capex and opex. So the operational costs aren't exactly reliable. So they do struggle to compete with the current fossil fuel sources of hydrogen available globally. In terms of operational flexibility, there's this need to continue to design electrolyzers to be more coherent with being linked to renewable energy sources such as your solar and your wind. And currently, number 3 over there, one of the drawbacks with a lot of hydrogen systems is the complexity that's involved. And obviously, we have more components and more complex components. The manufacturing process obviously needs to come into play in order to streamline the manufacture of these electrolyzers as to reduce the capex. So you've got 2 choices there: either do streamlining on the manufacturing side or reduce the complexity of systems. So those are the current industrial challenges. Moving on to the next slide. So what do we have as Hydrox to bring to the table? So like I've mentioned, our core development is the divergent electrode flow through principle. And what's unique about it is it does not utilize a conventional membrane or diaphragm to achieve separation of the produced hydrogen and oxygen gases. So quite simply, we believe that the absence of the membrane will allow for operational flexibility as well as the improvement in the high capex costs associated with currently available conventional electrolyzers. And in terms of our advanced alkaline electrolysis system that we're currently developing, it makes use of industry's best components such as membrane separator components from AGFA, as well as electrodes sourced from Denora. And the whole idea about that is to simplify and streamline the electrolyzer design while achieving a high efficiency. And again, the whole idea is for us to incorporate this technology as an OEM manufacturer here locally in South Africa. Moving on to the next slide. All right. So just a bit of a breakdown in terms of what distinguishes the difference between the technologies. So our core technology, which is DEFT, as I've mentioned, it doesn't make use of any kind of membrane to separate the oxygen and produced hydrogen gases. It slowly responds on the flow of electrolytic solution through porous structures in order to maintain the gaseous separation. So as a result, there's a small electric gap that's present inside the electrolyzer itself, but there is no conventional membrane or diaphragm. And flow introduced into a cell provides you the unique advantage that you do not have to such extent, concern yourself with too much ohmic resistance formed by the gas bubbles on the electrode surface, because they're actively removed from the cell all the time. So you have that benefit in terms of being able to now achieve very high current densities and not being limited by the current density threshold that you would normally have with an alkaline technology. And the whole idea with DEFT is to enable us to push the conventional boundaries of current conventional electrolyzers. And on the next slide, I'll illustrate to what extent the technology can go about achieving that. In regards to our advanced alkaline electrolysis technology, so it's an advanced technology, aims to use a zero gap type operating principle, but the whole idea is we want to develop a reputable advanced electrolyzer that can obviously be commercialized here locally, and that would be our current short-term route to achieving commercialization. To DEFT, what I'd like to go through there is just in regards to the potential that we see with DEFT when it comes to penetrating the market. And the first is the unique potential for us to open ourselves to medium temperature operation. The idea here is to do something that has previously not been successfully achieved in terms of commercial space, but to operate an electrolyzer within the temperature range of 150 to 300 degrees Celsius. So what's so good about that? You'll be able to save a great deal of your electrical energy, as much as 30%, because your enthalpy of reaction at the end of the day is provided by electrical energy as well as by heat energy. So that's what's so exciting about medium temperature operation for DEFT. Likewise, we see a lot of potential in terms of demonstrating DEFT utilizing different electrolytes. So using urea electrolysis, which is great because you only need a very low equilibrium potential in order for the reaction to be spontaneous, and contaminated water source. So there is potential for it to be used in treating acid mine drainage, for example. And what's nice about that is we don't suffer the same drawbacks as what a membrane or diaphragm would when placed in these very aggressive environments. Number 3, dynamic load operations. So it's something that we've already tested in a demonstration of technology that we've done recently, in terms of being able to extend to higher current densities as well as having dynamic load operations. So there is literally no possibility for our cell to suffer thermal failure or heat spots conventionally associated with membranes and diaphragm, simply because there is no conventional membrane or diaphragm. And high current density operations, so we're currently working with Duke University in the United States that are busy developing very unique high density electrodes for us in order for us to extend our current densities to levels previously not operated with alkaline water electrolysis. And this is possible due to the reduced cell resistances and better mass transfer characteristics associated with the technology, which makes it very unique in its own right. Over time, we've done a number of concept demonstrations to go about developing our unique technology DEFT, and we've obviously done this on a number of stack prototypes over time. And we've worked on this technology for the past 8 years, and it is currently ready to extend itself to potentials not recently realized by conventional electrolysis technologies. And this is really what we would like to explore in a number of partnerships that we're looking at the moment. But just to summarize where we are with the technology, just waiting for the slides to catch up. I think it's caught up. So on the left-hand side, we've recently done a demonstration of our technology for Shell, the Game Changer program located up in the Netherlands. And the whole idea of this technology was to demonstrate our DEFT technology on the basis of producing a unit that can do 2.5 millimeters cubed of hydrogen per hour. So it roughly equates to a sizable demonstration stack of roughly in the range of 15 kilowatts. And that operates off our DEFT principle. And as I've mentioned, concurrently, we're busy developing our advanced alkaline electrolysis technology, which utilizes a lot of the core elements that we've incorporated in our DEFT technology, alongside the AAE and utilizing the core elements. We obviously utilizing our own unique experience in order to go about designing a very competitive unit here. Moving on to the next slide. So just to go briefly over what our Game Changer program was about. So we were commissioned in June 2018 to undertake a project to do a demonstration. Project was briefly subdivided into 3 phases. So the technology had some challenges associated with it, which we obviously had to overcome in phase 1, which graduated us over to phase 2, which was the engineering. So various different safety checks, hands-off analysis in order to produce not only the stack itself, but the complete balance of plant, which we all did the design internally within Hydrox in order to facilitate a unique balance of plant in order to operate such a unique cell. And in phase 3 was obviously the phase that we went about fabricating, testing, and commissioning the unit inevitably. So that was our Shell Game Changer, and from Shell Game Changer there came a number of outcomes. So the technology is still very much in a rudimentary form. There's still a lot of optimization that we can do since it is largely uncatalyzed at the moment, but it shows good potential in terms of getting to very reasonable efficiencies. And with our Shell Game Changer project, we managed to demonstrate an efficiency range of roughly 64 to 68 kilowatt hours per kilogram of hydrogen. So on a high heating value, that translates into a percentage range of around 62 to about 58. And we demonstrated the stack within a voltage range range of 1.8 to 2.4 volts. A little bit higher than conventional alkaline electrolysis technology, but we have the aim to bring it into the region of 1.7 to 2 volts in the near future. And regarding the combined capex and opex costs with an assumed electrical production cost of $0.07 per kilowatt hour, we calculated the end cost to produce hydrogen from our system produced at atmospheric pressure to be in the region of about $8.44 to $6.95 per kilogram, depending on where in the voltage range you go about operating. So we feel there's still significant potential to go about improving that cost range. And in terms of achieving the gas purities, we had to achieve anything in the region of 99.5 volume percent and higher, which is great because we managed to achieve that with a membraneless principle, and we've demonstrated that we are able to go about achieving good gas purities, very similar to what you get from a conventional alkaline electrolyzer. And in terms of scale up, so previously we started very small, but with our game changer unit, we're able to provide a demonstration in the region of 320 millimeters in size. So what are our next steps to go about concluding? So we would like to continue with the development of our DEFT in order to incorporate it into all the various different areas of potential that we see fit. We'd likewise like to scale the technology to much larger sizes, in turn improving the operational overall efficiencies of the system. And with regards to point 2, we're obviously doing our development of our advanced alkaline electrolysis technology concurrently in order to commercialize and to actually bring our business into the commercial space. And the goals that we have over there for the technology, we feel is very achievable. So we would like to get efficiencies into the region of 79 to 66% on the high heating value. And we'd like to do a demonstration roughly in the region of about 250 kilowatts. And inevitably, we would like to prove and show that we can bring the cost to produce hydrogen below $5 per kilogram. So that pretty much concludes my presentation. So I see there is a couple of questions. Oh my goodness, okay, I'll read that question out in detail, but just with more information, that if you'd like to learn more about our developments, or if you have a keen interest in hydrogen, we encourage you to get in contact with us, and you'll see the contact details on the screen.
Okay, thank you, Malcolm. Yes, we do have some questions, but please keep them coming into the questions box, so we'll get for as many as we can. So, being an expensive process to operate, what will be the main customers, and will the process be commercially viable in terms of the payback and revenue generation?
Sorry about that, Matt. What did you mention? The customer basis? Sorry, it just broke up a little bit there.
Who is the customer base, and is it commercially viable in terms of the payback and revenue generation?
So hydrogen as itself is, you've got the renewable spectrum, but there's also a very large existing industrial base for the use of hydrogen. So when it comes to basic hydrogenation reactions, with the production of methanol, hydrogenation of foods, there's a large basis for it in the electrical industry, in the glass manufacturing industry, largely in chemicals manufacture, as far as I believe. Ammonia is the massive one when it comes to the usage of hydrogen. So yes, there is a very much demand for hydrogen currently in existing industries, but a lot of the new industries are coming on to the focal point, which is in regards to transportation, so making use of fuel cell electric vehicles. I know semi-trucks are increasing in popularity within Europe with regards to Mercedes-Benz, with regards to Nikola Motor Groups within the United States. So indeed, there are new applications coming on, and more so for green hydrogen as well as for carbon neutral hydrogen. So there's a lot of demonstrations happening in the mining sector as well with regards to fuel cell electric vehicles. But when it comes to the whole production of e-fuels, so utilizing CO2, carbon capture, and obviously utilizing the hydrogen in that sense to produce e-fuels in the form of methanol is a very large drive in terms of that. And to answer the question when it comes to the potential to be commercial, to actually be profitable, at the end of the day, when it comes to electrolytic hydrogen, one of the key things that does come down to the economics of that particular and right now, when you look at steam ether reforming, you are capable of producing hydrogen in the region of $1.5 to $2 per kilogram of hydrogen. So there are very large forecourt electrolysis systems that are currently knocking on the doorstep of being cost competitive within that region, but you need to obviously compare or be better than that to actually be able to take the market completely. But there is very large applications and interest in decentralized hydrogen production by means of electrolysis, because a lot of hydrogen is busy being produced centralized. So I hope that answers the question. And when it does come to our technologies that we're producing, we do aim to actually eventually make a move to improve the costs when it comes to electrolytic hydrogen. Otherwise, we wouldn't be doing what we're doing. So I do hope that is a good answer to that question.
Okay, thank you. It's mentioned that you're planning further optimization on the hydrogen gas quality for a range of parameters. Can you elaborate on this?
100%. So what I'd like to make mention to there, Matt, is right now we have proven that we can produce adequate gas qualities as what per the conventional electrolyzers can do in industry, but where a lot of the gas qualities suffer with regards to the turn down ratios, and the same could be said with regards to our technology to extend the ability for the technology to produce pure gas on a broader experimental parameter range currently possible by conventional electrolyzers. So in the very low temperature spectrums, and for example, in the higher temperature spectrums as well, where you'd find a lot of the components, for example, the membrane of the separators, otherwise failing within these conditions, so that you can truly take advantage of the high efficiencies that you can go about achieving in the higher temperatures range. So yes, there is further optimization that we need to perform within our technology, and you need to take cognizance that the technology is flow rate based, so you would get low gas qualities at low flows. So the whole idea is you need to do an optimization with regards to the flow dynamics of the technology as well, in order to actually have something that can prove good gas qualities across a very broad experimental range. So I hope that that's answered. So there's still some work and some challenges with regards to the technology that we need to address.
Okay, thank you. I'm afraid we are out of time for questions. We do need to move on. So thank you very much, Malcolm. It is now time for our third finalist, and representing the joint entry from the Norwegian University of Science and Technology, North Carolina State University, and Sintef Industry, please welcome Richard Spontak.
Can you see my screen, Matt?
Yeah, we can see your screen and we can hear you nicely.
Wonderful. Well, good morning, everyone from the United States. It's a great pleasure for me to present this work on behalf of the Norwegian University of Science and Technology, Sintef Industries, and North Carolina State University. We're going to be considering now organic membranes that are engineered from the ground up for ultra-selective CO2 separation, and the people who have really been instrumental in maintaining this research, Professor Liwan Deng from NTNU, Dr. Marius Sandru from Sintef Industry, and myself. So with that idea in mind, first I'd like to set the stage, because we all hear about global climate change. We hear about how important CO2 removal and capture is. So let's kind of put things in perspective. And let me see if, there we go. Okay. So first thing is that if we look at reports by agencies such as the Intergovernmental Panel on Climate Change, this came out in 2018, what we see is indisputable evidence that due to humanity's interactions with the environment, which are referred to as anthropogenic activities, we do in fact see a general increase in global temperature. And the most warning part about all this is the extrapolation from 2020 to, say, for example, 2040. And so the break point in this curve has been identified at 1.5 degrees centigrade. That is where we will start to see considerable problems arising due to this type of climate change. And as the IPC rightfully pointed out, there are a variety of aspects that need to be considered when we look at this type of phenomenon. So here are a variety of different risk assessment factors that we should be looking at. And of course, we often hear about the corals being affected by climate change. And yes, they are very susceptible, as of course the Arctic regions. But let us not forget about, for example, fisheries or coastal flooding, or even crops. And lastly, our own health and our mortality. So these are all interconnected. These are not to be differentiated. This is an integration problem. And so we need to start thinking about it as a system-wide issue. And we even see now some of the telltale signs of the climate change issue when we look at for example, the fires that are engulfing the western part of the United States or Australia, when we start to see regions that were once flush becoming arid, or we start to see superstorms developing on a much more routine basis in the Atlantic Ocean or the Pacific Ocean. And lastly, of course, we see the slow demise of the Arctic regions. And for those who think that this might just be due to increased solar activity, NASA has shown that that is not the case at all. So this is within our hands, which means that there is a need to remove CO2. Now, these are based on our environment, but there are other reasons for removing CO2. You heard Malcolm mention steam reforming and the water gas shift reaction as being the primary current source for hydrogen. In that process, there requires removal of CO2. What about also considering air filtration or air purification in confined environments, such as those that we would encounter in underwater operations, or as it becomes more apparent that there's interest in extraterrestrial travel and perhaps future colonization of the moon or Mars. So we have the rationale for doing this. What are the approaches? There are a variety of different ways in which one can remove CO2 from mixed gases. One of the most common ones involves CO2 philic solvents. And these can be aqueous or non-aqueous amines, but they rely on one important characteristic, and that is high CO2 solubility. Unfortunately, these types of liquids can also be toxic, corrosive, etc. Then we could talk about inorganic membranes, where we deal with designing materials that are typically nanoporous, and we work with size selectivity and absorption. Problems, of course, they're fragile. They can be tailored, but they tend to be expensive. Organic membranes, well, they can be size selective or solubility selective, and they tend to be much more mechanically robust. They're tunable in terms of properties, and most importantly, they're scalable. So I'm going to be spending time talking about these, but let me just point out, for the sake of completeness, that one can take this idea and put it into a unit operation cascade, so we have a sequential process whereby we take these membrane modules and basically run them through to try to get to the purity level that we want. Now, I'm not going to be talking about this, but one can easily envisage taking what I'm going to be talking about and putting them into this type of process. There are two important metrics that we need to consider. The first one is the CO2 selectivity relative to another gas. We're going to typically look at CO2 selectivity relative to nitrogen, since this is an indicator of air. And a lot of the work that has been done has really been looking at, for example, flue gas or those types of CO2 removal processes. And then lastly, we want to consider permeability, because this, of course, is a measure of throughput. So with those in mind, let's turn to the first of two different strategies that we've developed. The first one is based on green technology. And we thought that it would be an interesting starting point to look at a system that exhibits low selectivity for any gas, let alone CO2, and low permeability. So what we're looking at is a barrier material. And one of the best barrier materials that occurs naturally is nanofibrillated cellulose, or NFC. And so what we're going to do is we're going to open up the nanofibrils of NFC by introducing a CO2-philic ionic liquid. Well, ionic liquids also tend to be hydrophilic. So we're going to also try to tune the sizes of these channels and their solubility properties through the introduction of moisture. And that's going to be controlled through relative humidity. So this schematic basically gives you a quick overview of our hypothesis. Namely, we start off with a material that's a barrier, and I think it's only appropriate that this fence be made out of wood since we're dealing with nanocellulose. Then we start to open up the gate, and by doing so, we allow only CO2 to get through. And then lastly, if there's too much separation of the nanofibrils, then we see everything getting through, and now we essentially lose our selective transport properties, but we have a lot of throughput, and the nanofibrils really serve more of a mechanical reinforcement role than a transport role. So here are some images to show what the nanofibrils look like. This shows what the nanofibrils look like when they are put in contact with the ionic liquid, which is 1-ethyl-3-methyl-imidazolium acetate. And then we can look at some STEM images that show, once again, we have the nanofibril, that's the real space image. This is an energy dispersive spectroscopy image that tells us that, yes, as expected, the nanofibril is composed of carbon. And the last one is a nitrogen map that corresponds to our ionic liquid, and that too is corresponding to the nanofibrils. So this provides direct evidence that the ionic liquid does have affinity for those nanofibrils. Well, once we start putting in the ionic liquid and introducing relative humidity, we find something that's very, very interesting. And that is that when we look at the permeability of CO2, we find that as we add in both moisture and ionic liquid, we see increases in the permeability. Not initially though, but at some point, we see a break here where all of a sudden the permeability starts to shoot up. And we're talking about permeabilities going from about 100 bar or less to now about 300 bar. But that's not the exciting point. The exciting point is looking at the separation factor. These measurements are for mixed gases. It's important to realize that we're not just looking at CO2 and nitrogen. We're looking at a mixture of the two. And what we find is that in this range over here, that's colored somewhat salmon, we see that essentially we have a barrier type material that has relatively low selectivity as indicated by the separation factor. So these are based on measurements obtained from gas chromatography. But within this green range, we see a spike in the separation factor and hence the selectivity. So this occurs at an intermediate value of ionic liquid and an intermediate humidity. This is our gate opening mechanism. Once we get past this, however, if we add in too much ionic liquid, we see that we actually lose our selectivity. Permeability still increases, but the selectivity does not. So there's a sweet spot in here where we can now look at ultra selective membranes where selectivity now is greater than 100 for CO2 to nitrogen. The second strategy is looking at integrating membranes into a layered system. So the difference here is now that we start with low selectivity but high permeability membranes, and these membranes can use some very well-established materials like polydimethylsiloxane and polytetrafluoroethylene in the amorphous form. So this is essentially Teflon, but it's amorphous Teflon. And that allows us to obtain very high permeabilities but low selectivities. And the idea here is that if we look at traditional ways of producing organic membranes, they can be self-standing, so that we're looking at thicknesses on the order of about 50 microns, or they could be supported by a macroporous support. And now we look at only thin films that measuring maybe about 1 micron, so they do need mechanical support. What we're looking at is taking this idea and extending it one further. And that is, we're going to decouple the properties of this supported layer such that we now have a high permeability layer and a high selectivity coating on the surface. And this coating is only about 10 nanometers on the order up. So what we see within this range now is along the surface, we have species that are highly hydrophilic and they are highly CO2-philic. So amines, which you heard me mention earlier, are perfectly suited for this. Water stays within this range and allows us to take CO2 at one concentration and build that concentration level so that now when it goes through this high permeability zone, it's now much more highly concentrated, and this is what we remove. To give you an idea of what this looks like, here are some SEM images showing before and after our coating on top of the Teflon amorphous fluoropolymer. And you can see that initially we start off with a few holes here and there, but over here, what we're seeing now is a pretty conformal coating. For PDMS, we start to see some regions that show that the surface is not exactly heterogeneous, but upon closer examination by AFM, we can certainly see that there are nanoscale droplets of our coating on the surface. And now this provides a very rough surface where we have these CO2-philic groups available to capture the CO2. And what we find is that if we start off with either the high permeability Teflon or PDMS, and we coat it appropriately, we can drive the selectivity up by almost 2 orders of magnitude. So now we're in this range for these types of materials. And if you compare that to the Robeson upper bound limit, you see that we're well above that, and even above the limit that was established for polymers of intrinsic microporosity, which was introduced last year. So we have highly selective materials. They're just slightly more selective than that the cellulose materials that I showed you earlier. So in conclusion, and I hope I stayed within time, these are some of the people who were involved in this research at each of these partnering institutions. This was a very synergistic effort resulting in both papers and patents. And so I would also like to point out that this work was supported largely by the Research Council of Norway, by Horizon 2020 from the European Union, and at NC State from our College of Textiles, from Eastman Chemical Company, and our National Science Foundation. And I included here that graph at the end to show once again where our ultra-selective membranes are located. And we actually do get into the Goldilocks range over here, where we have high permeability and high selectivity. On that note, thank you very much for your attention. To reiterate, we are highly honored to be selected as a finalist in this competition. And if anyone would be interested in talking with any of us, our contact information is provided here. Thank you, Matt, and thank you again to the Institution of Chemical Engineers.
Okay, thank you very much, Richard. It's time for Q&A, so we have a few minutes. If you do have a question, please type it into the question box on the GoToWebinar portal. Our first question is, how do we get the desired gas by adjusting the permeability, humidity, and other factors to ensure the CO2 is attained?
So what we want to do is, it depends on which approach we're using, okay? So that's very important. Whether we start off with the cellulose approach and starting off with low permeability, or introducing the high permeability route. And because you mentioned that you're interested in looking at the humidity, I'm going to assume that we're only talking about the first approach. So in that particular case, there is an optimization, okay, which is typically the case for many chemical engineering problems. And in that optimization, what we're trying to do is we're trying to find the conditions that lead to contiguous channels of ionic liquid that can be slightly swollen with moisture. So to find those conditions, what we opted to do initially was to simply look at low concentration of ionic liquid, intermediate, and high. High for us was about 50%. But what we found was that when we were at the intermediate levels, where we were starting to see just enough of a broadening of these channels between the nanofibrils, when we were at too low a concentration of ionic liquid, it really didn't do much. It did a little, but not much. But when we got to a level where we started making the channels a little bit larger, and we started to introduce, and that's why we showed the data as functions of relative humidity, we found the sweet spot where we could actually use both the solubility, the high solubility of CO2 in the ionic liquid in conjunction with that of the water that was present in the channels to help drive the preferred permeability of CO2 relative to other gases. And I didn't show it here, but we did look at other gases. So we did look not just at nitrogen, but also helium and methane. And so we saw the same effect that we saw with CO2 relative to nitrogen, that there was significant selectivity enhancement in that sweet spot at intermediate levels of ionic liquid and relative humidity. I hope that answered the question.
Thank you very much. We'll take one more question. Has this technology started scaling up and gone to commercialization?
To the best of my knowledge, it has not yet, because it's actually ongoing. It has certainly undergone some intellectual property protection, but the idea is still moving forward, and we were very excited actually to see these levels of selectivity obtained from two very different starting points, but nonetheless through some type of modification, whether it was to open up the nanostructure of the nanofibrillated cellulose, or to introduce specific CO2 specific moieties on the surface, we found that both approaches actually got us to where we wanted to be, which was in the high CO2 selectivity threshold. So I'm anticipating that because of the ease by which both approaches can be further developed, and also the fact that the high permeability membranes are already commercially available, and the nanofibrillated cellulose is a green and sustainable material, I don't see any barriers by which these types of approaches would have problems being commercialized.
Right, thank you very much, Richard. We need to move on, so thank you for your presentation.
Thank you.
Thank you. And our next finalist has sent us a pre-recorded video. So this is a pre-recorded video from Petronas.
Even though self-healing technology has been developed for many years, commercialization still remains a challenge due to the expensive catalyst. Our breakthrough innovation replaces the rare earth-based materials with metal organic frameworks, which are more sustainable and economical, thus allowing upscaling and commercialization. The partnership between Petronas, Deakin University and University of Adelaide is proof of a successful collaboration between industry and academics to take this technology further.
We all know that infrastructure in the oil and gas industry is very costly to maintain and to keep safe for workers. So we believe there is an opportunity to use self-healing materials to extend service life, lower maintenance costs, while at the same time enhancing user safety. The technology that we've developed with Petronas and the University of Adelaide addresses the long-standing problem of latency in self-healing materials. Using traditional microencapsulation techniques and a new application for metal organic frameworks, we've been able to greatly increase latency and durability while achieving high levels of healing by eliminating surface defects to maintain the integrity of the coating and thus preventing corrosion.
Self-healing materials allow cracks or damage to repair itself without external intervention. In GRNT, we have successfully developed patented self-healing technologies that aim to improve performance and extend the service life of the materials.
Okay, that was a pre-recorded video, so obviously no Q&A. So we'll move straight on to our presentations from Saudi Aramco now. So first up is Noof Jabri from Saudi Aramco Expec ARC. Over to you, Noof.
Hello?
Hi, Noof. We can hear you and we can see your screen, so that's great.
Thank you very much. Thank you very much. So thank you for the introduction. On behalf of my colleagues, I would like to thank the organizers as well as the valuable committee member for their great efforts to have such a prestigious event. We are really honored that the nanotags entry has been shortlisted for the oil and gas category. So ladies, gentlemen, through this presentation, we will introduce to you a revolutionary technology called nanotags for improved drilling cuttings depth and high quality mud logging formation evaluation. During the drilling operation, the drill cuttings are made by the drill bit and then transferred to the surface where it can be collected from the mud shaker. These drill cuttings provide petrophysical information about the formation at the depth estimated from the mud logging and help us to understand the formation's lithology. And as a result, we can optimize the well placements to maximize the oil recovery. Furthermore, the cuttings would tell us a lot about the hydrocarbon content, which leads to improve the reservoir management practices. And based on this, we can have a general agreement that these cuttings are very, very valuable to us to enhance the production. However, the key challenge to maximize the value of cuttings for real-time formation evaluation is the accurate determination of the cutting's depth. Unfortunately, the mud logging deployment has historically suffered from limited application due to the uncertainties in the drill cutting's depth determination that can be reached to plus minus 15 feet, as you can see. This is already huge, and this uncertainty can be caused by many factors such as hole caving, hydraulics, gravitational debris accumulations, and many other reasons. And of course, this huge uncertainties leads to lack of a proper reservoir characterization and formation evaluation. And as a chemical engineers working for oil and gas company, we developed a technology called nanotags. This nano tags working to tag the drilling cuttings precisely as they are made at the drill bit face. That they are generated at the drill bit with barcoded nanotags that are injected into the drilling fluid. So these nanotags will be injected in certain sequences and concentration with the drilling fluids and travel there to label the drill cuttings, and then the labeled drill cuttings will be collected from the mud shaker, as you see here. And this technology can reduce the uncertainty to plus minus 1 foot. And the generated cuttings will be permanently labeled based on their depth of origin without affecting any of their properties. I'm trying to move to the next slide. Yes. So this is an illustration of our developed hybrid process combining flow mixing with batch polymerization, flow to batch method, to produce the nanotags at a rate of 1.8 liters per hour in the lab. The synthesis of the nanoparticles via the low surfactant loading or a surfactant-free emulsion polymerization is very simple, scalable, and cheap, both in a small batch as well as in the large scale state-of-the-art flow reactor. The size of the as-made nanoparticles are narrowly distributed in the range of 20 to 60 nanometer in stable colloids that have a shelf life greater than 1 year at ambient conditions. And the innovative nanotags are designed to be compatible with the water-based drilling fluid via addition of the hydrophilic comonomers or ionic surfactant. This compatibility can be further adjusted via the reverse emulsion for the use in the oil-based drilling fluid as well. Worthy to mention that the hybrid nanotag synthesis process using very safe microreactors, and the whole process was optimized for a safe operation. We designed a unique drilling depth correlation system consisting of the nanotags that you see in the containers in here and the automated injection system, as well as the detection and separation workflow. The nanotags are transported to the field in low concentration aqueous suspension. It's only like 1% concentration, so it's very diluted, and is used at a ppm concentration. And here we are talking only about 5 and 10 ppm concentration of this material introduced to the huge mud tanks in the rig site. The injection system will add the nanotags at certain pulses and concentration before the low pressure point in the mud line and operates under explosion proof conditions to prevent any interruption for the drilling operation. So we can do this kind of tagging for the drilling depth precisely without interrupting the drillers or the drilling operation. And later the cuttings will be the cuttings were tagged as they were drilled at the drill pit and then collected off the shell shaker. After that, the collected cuttings are exposed to a solvent extraction and thermal separation workflow to extract the nanotags from the cuttings in the lab for estimation of arrival times. Since the nanotags undergo thermal depolymerization, every tag would show us a very unique characteristic that can help us to know from which depth this cutting came from. So now if your question, if that is a dream of chemical engineers or this is for real, actually we have tested this material in December 2019. So basically we have celebrated the Christmas in one of the Saudi Arabian fields. The first deployed of the nanotags to label the drill cuttings in carbonate reservoir. We successfully injected ppm levels of different nanotags into the mud line without any interruption of the drilling operations. The cuttings were tagged as they were drilled at the pit and then collected off the shell shakers. We used the developed solvent extraction and thermal separation workflow to extract the nanotags from the cuttings in the lab for the estimation of the arrival time. Systematic differences observed between depth estimated from the downward nanotag travel time versus the conventional method using that the mud loggers are using. And the results actually shown a clear example of unintentional borehole enlargement that is a systematic error that the nanotags technology can correct for. The pyrolysis GC mass detection of the nanoparticle is especially beneficial for the unconventional reservoirs that need to use cutting to determine from total organic carbon, corrosion, bitumen content, as well as the maturity at a precise depth. To sum up, a barcodable polymeric nanoparticle design as tags for drill cuttings were synthesized and tested in the lab. A drilling field test confirmed the compatibility of the nanotags to determine the exact depth of origin of the drill cuttings in real time. And the impact of this is that the nanotags approach has potential to be a game changer in the oil industry, allowing accurate and precise cutting depth determination for real-time characterization from the cuttings. An analysis of the drill cuttings allows to measure the properties of the underground rocks and the fluid content evaluation and to improve the reservoir management practices. Thank you.
Okay, thank you very much. Once again, we have a few minutes for questions. So if you have a question, please type it into the question box on the GoToWebinar panel. Our first question is, can you please elaborate on the process you use to adjust the nanoparticles when drilling in water? And when in an oil environment, what is the best favored environment for maximum production?
I'm sorry, would you please elaborate which process you mean, like the injection process or the detection process or the overall process?
The question reads, can you elaborate on the process you use to adjust the nanoparticles when drilling in water? That's the first part. And then the second part, when in an oil environment, what is the best favored environment for maximum production?
So this technology has been developed for drilling oil wells, not water wells. So oil and gas. So basically hydrocarbon wells. So and we tested them in one of the gas wells as well. So I'm not quite sure if that will be relevant to drilling a water well. But what is important for this technology is that when you drill in a reservoir, regardless if it's oil or gas, it will be really important to know from where these cuttings, the drill cuttings, came from which depth. because each depth has its own hydrocarbon content, has its own, the quality of the hydrocarbon is different from layer to another layer. So it's really important for us to know where these cuttings came from, so we can maximize the production from that certain zone. And also, it's important for us to improve the reservoir characterization. Since we know now this layer, for example, has a very high quality oil, then we will place the wells in the right zones to maximize the contact with the reservoir, if that can answer the question.
Okay, thank you. Next question. Is this technology only suitable for a certain soil mixture, or can it be adopted globally where the soil mixtures are different to the one in the Kingdom of Saudi Arabia?
It's absolutely, it can be like a universal, would say like either any water-based drilling fluids or oil-based drilling fluids. This material or these nanotags can work very well for it.
Okay, then, thank you very much. It's time to move on. So thank you for your presentation.
Thank you very much.
We're now going to move on to our next finalist. Once again, representing Saudi Aramco, please welcome Mohammed Amanullah.
Hello. Hello.
Hi, yes, we can see your screen and we can hear you clearly.
Okay. Good afternoon, ladies and gentlemen. My name is Amanullah. I will be talking today. We have developed a couple of novel drilling fluid additives using waste materials available in the kingdom. So we'll be talking about this development. To proceed to next slide. This slide shows the research team member, my colleagues who contributed in this research. Other than myself, my colleague Dr. Mohammad Arfaz, Rayed Alahali, and Dr. Jyoti Basu was involved in this research. Now, the first objective of this research was to application of locally generated waste materials for localization of product development to replace equivalent imported products. Currently, we are importing all our drilling fluid additives from overseas countries. So purpose was to develop locally using locally available resources so that we can replace these high cost imported products, promote local industrial growth and create new avenue for revenue generation and fulfill corporate and citizenship charter. The second objective was to solve several industry problems simultaneously. The waste material is generated by other industries. As for example, we use the waste material generated by date palm industry, automobile industry, and food and catering industry. So that was a recycling. One industry was to develop some value-added product for using by other industries, as for example by the oil and gas industry, and also to promote multi-sectoral collaboration and joint ventures to solve some of our industry problems. And finally, the objective is to have positive economic and societal impact so that we can contribute in the local industrial growth, creating new jobs, and also contributing the economic development of local communities. The product development strategy, that we can develop product using some waste material, but in the process of manufacturing this product, if we generate another waste product, that is not good for the environment. So we adopted a method that is eco-friendly method that we call. That means it is not generating a waste material, or the waste material it is generating also can be used as a product or byproduct. And it will create a sustainable source of supply for the kingdom, so that in any geopolitical situation or natural calamity, as for example now due to the COVID, we are unable to import lots of these materials. Now, if we developed it locally, we'll be able to avoid this type of problem in future. First, I will talk about the date palm industry waste that we used to develop couple of products. These are called conventional LCM product, but low circulation material. As you can see, a date palm industry, from a date tree, there are various components of the date trees. We used all the component of waste date trees to develop three major products that is used by the industry for the last 100 years. And we are importing this product since starting of the oil and gas exploration. Now, we developed this product locally using this waste material. First, we used the date seed. That is, after eating the date fruits, the seed coming as a waste materials. In this country, we generate huge amount of date seeds, more than 250,000 tons per year, and nobody knows what to do with it. So our objective was to solve the disposal problem of the date palm industry and create a value-added product for oil and gas industry. And that's why using the date seed, we developed a product that we call arc plug. It is a particulate low circulation material. So far, we imported this type of product from overseas countries and commercially known as nut plug, Mexico plus, different company has different names. We developed using the date seeds as the raw material arc plug. And this arc plug we tested in the laboratories, evaluated, and field trial tested in the field. It has superior performance than the commercial equivalent products. Then, secondly, we use the leaflets and the fruit caps coming from the date fruits after eating it, and the leaflet as coming as a pruning waste. We use this material to develop another product that we use for controlling loss of circulation while drilling, called flaky LCM, flake type LCM. So we use this material to develop the flake type loss circulation material, particulate, flaky, and fibrous. These three loss circulation material are the major loss circulation material used by the industry since the starting of exploration and exploitation of oil and gas resources. Finally, we use the disease date tree and all the root and trunk, everything of the disease date trees that to create or develop some fibrous product, fibrous low circulation material. We call it eco fiber because it is natural, it is organic, it has no detrimental impact on the surrounding environment. That's why all these three products are eco-friendly products. So there will be no environmental impact if we use in onshore, offshore, in lagoon areas, in lake areas, whatever. Now, the three product we have developed, one is arc plug. This is particulate low circulation material. Another arc eco fiber. This is fiber low circulation materials. Another is arc eco flex. This is flaky low circulation material. As I told before, these three major classes of low circulation material is used by the industry since the starting of the oil and gas exploration, and we are using now and probably will be using until the oil is finished. So, and this arc plug, now all commercially available product available currently in the market, we can replace by using our arc plug, which we developed using the date seed. This arc eco fiber can replace all fibrous product that is available in the market and marketed by various companies in different trade names. And the arc ecoflex that can be used to replace all flaky LCM currently in the market. The two products, arc plug and arc ecofibers, already commercialized by Aramco, and it is now used by Aramco, and we stopped importing the imported product that we imported before. The arc ecoflex in the pipeline, we are trying to form a spin-off companies or a partner for commercialization, and business development. The second product we have developed using the waste scrap tires. There are lots of scrap tires available in the kingdom, scattered in the desert areas and everywhere, and nobody knows what to do. So we try to develop a product using this material. Currently, we use a resilient LCM product that is imported from overseas countries and made of graphite. That is a graphite-based resilient material. This graphite-based resilient material is very costly. And that's why we try to develop a resilient LCM product that can replace the high-cost graphite-based resilient LCM product. And we developed these several grades of these LCM products, coarse, medium, and fine. And then we tested and evaluated in the lab, and this product shows similar performance like the graphite-based resilient LCM product. So we can reduce the cost of a fluid design by 10 to 15 times if we use this product compared to the graphite-based resilient LCM product that is commercially known as steel seal or lube, lube glide, like different names. But this product now are able to replace all these products. And recently we have done a trial test of this product in combination of this other product we developed, and we have completed the successfully a trial test to control the total loss of circulation. The final product that we developed, some eco-friendly lubricants. As you know, most of the lubricant currently we use in the industry is coming from diesel or mineral oil based or their derivatives. And these guys are not good for the environment. And it can cause damage to the offshore, onshore, or the marsh area, lagoon area, and kill all these other resources. So when we are going to explore and exploit oil and gas resources, if we are going to damage other resources, that is not good. And nowadays, different local, federal, and the state government are increasingly enacting environmental rules and regulation, and we are restricted to use this mineral oil based or diesel oil based product. So we need the eco-friendly alternative. So using waste vegetable oil, we have developed some eco-friendly lubricants and emulsifiers. Now, why we use waste vegetable oil? Because this is a waste product. There is no other use for the food and catering industry. But the fresh vegetable oil, if we use the fresh vegetable oil, we will be taking a big chunk of the oil from the consumer market, and that may have a negative impact on the consumer market. And that's why we switch to the waste vegetable oil that will solve the problem of the food and catering industry, their disposal problem, and that will solve our problem, that alternative to non-eco-friendly mineral or diesel oil based lubricant we can replace by developing some eco-friendly lubricants using waste vegetable oil. Sorry for that. And now we have developed a couple of lubricants using this waste vegetable oil, and we tested in the lab. And this lubricant is performing similar to the commercial lubricant, which is highly costly, commercial eco-friendly lubricant that is highly costly. And then we developed also a spotting fluid. Currently, the spotting fluid, probably some of this terminology, if you are not involved with the oil and gas industry, it may not be clear to you. This spotting fluid we use when during the drilling, some pipe is stuck, then we have to recover it. So this spotting fluid is used to recover the pipe, drilling pipe, if it is stuck. And we developed this eco-friendly spotting fluid to replace some of the non-eco-friendly spotting fluid currently in use. And also emulsifier. We have developed a eco-friendly emulsifier to develop oil-based mud system that will have minimum impact on offshore and onshore areas. Now, what will be the benefit of this eco-friendly product. Actually, all these products that we develop, the eco-friendly, environment friendliness was one of the factor. Localization was another factor. Replacement of the imported product, that was another factor. Now, if we use this eco-friendly product instead of the non-eco-friendly diesel or mineral oil-based product, we'll be able to preserve the freshwater reserves, swamps, wetland, rainforest, coastal resources, shallow water resources, marine environment. So that we can protect it, we can explore and exploit oil and gas from these areas without damaging other valuable resources. Also, rig site safety for the workers is very important. Occupational health and safety is a very important part of oil and gas industry. So this use of this eco-friendly product will improve the occupational health and safety standard in the rig side. The another is the EPA, and the Environmental Protection Agency is nowadays enacting increasingly strict rules and regulation so that we are not damaging the environment. And that's why we have to fulfill their norms and standards. This eco-friendly product will allow us to fulfill the environmental norm and standard to be in the forefront of waste dealing practices. Now, this development already highlighted in several newspapers, several international, national newspapers. It was highlighted in the Arabian Sun, the Arab News, the Al Riyadh newspaper, Dimension International, and in the Middle East newspaper. Displayed and presented in Aramco booth in various national and international conferences. The waste vegetable oil based fluid, that this is, or these are all patented product, Aramco patented product, was selected in the 2014 AOC's annual meeting to extract, identify, and highlight the key information. Arc plug, arc ecofibers, and arc resi-LCM have been commercialized locally, and it has the potential to capture the regional and the global market. And the dead seed-based size particulate LCM arc plug won the Technical Innovation of the Year Award in 2017, High Impact Deployment of the Year Award in 2019. And finally, I cordially acknowledge the contribution made by colleagues and the technicians and the support for the expect management for this research, and thanks IChemE award committee members for selecting our research and development as one of the finalists. And that is the end of my talk. If you have any question, please.
Okay, thank you very much. We will pause for a moment to let you type in your questions in the questions box. And while we do that, let me just remind you that this is one of a series of IChemE Global Award webinars taking place throughout November. They're all free to attend and open to all. So if you'd like to find out what is still to come, visit our website, icheme.org/global awards. You may be particularly interested in our Energy Award, which is presented next Tuesday. So we have our first question. How did you offset the R&D cost of the development of these in-house developed products at the pilot scale before scaling up for larger operation production?
Okay. First, the lab scale production that we have developed in the lab as a lab scale product. And there is a local companies who has the larger scale facilities, but that is for other purposes. So we have a collaboration with this local factory now, who are now preparing or manufacturing this product for us in tons. So the facilities, everything is available locally to produce is locally, economically, and the raw material is as very cheap. The ultimate product is coming much cheaper than this commercial product that we imported before.
Okay, thank you very much. We are going to have to move on now in the interest of time. So thank you for that presentation. It's now time for our next finalist, and it's another Saudi Aramco entry. Please welcome Mubarak Al Rashid.
Hello? Can you hear me?
Yes, we can hear you and we can see your screen.
Thank you, Matt. Okay, good evening, ladies and gentlemen. My name is Mubarak Al-Rashid, and I'm one of the process engineers at Abqaiq plant in Saudi Aramco. I'll be sharing with you some of the details of how we restored our facility and global oil production following the terrorist attack on September 14th, 2019. Let me begin with telling you a little bit about the hydrocarbon processing facility that is Abqaiq plant. The facility is located in the eastern province of Saudi Arabia and processes up to 6 million barrels per day, amounting to approximately 5% of the global oil production and making it the largest oil processing plant in the world. The facility has a long history starting soon after oil discovery in the Abqaiq area of the eastern region of Saudi Arabia in 1940s. Over the decades since, the facility has grown organically and includes the degassing and stabilization of 3 different grades of crude oil, NGL production, as well as steam and power generation for facility self-sufficiency and exports. As I'm sure many of you will be aware, in the early hours of September 14, 2019, the facility came under fierce and unprecedented attack by aerial drones, directly impacting over 15 critical pieces of equipment, creating raging fire across the whole facility, and shutting down 5% of global oil production. Here, I would like to play a brief clip just to give you a taste of the intensity, ferocity, and resulting destruction.
أعلنت وزارة الدفاع السعودية وفي بيان من وزارة الخارجية Saudi Arabia says 2 of its oil facilities were attacked. Getting some breaking news out of Saudi Arabia. Major oil pumps in Saudi Arabia. استهدفت الطائرات مثل الطيار.
Gentlemen, based on the devastation caused, most commentators, including Bloomberg, expected months of disruption, but the reality was that production capability was restored in less than 2 weeks, and then sustainably maintained by 3 separate teams working around the clock to carry out the hard task of figuring out how on-spec products could be produced through the crippled infrastructure of the facility. This rapid restoration was carried out by prioritizing immediate recovery solutions to commence production, followed by efforts to ensure that the recovery was sustained and to ensure the specified crude grades can be supplied to our customers. Gentlemen, the prompt recovery was done for 10 stabilization columns that were impacted by the attack, including associated utilities and adjacent pipe racks. Over 25 procedures were developed to safely isolate, repair, segregate, and start up individual equipment after rigorous hydraulic analysis and relief adequacy check. 9 of the 11 degassing tanks were directly impacted. To commence maximized production, several of the tanks were patch repaired. This entailed a detailed risk assessment to operate the tank with derated design condition and the introduction of additional layers of protection. Furthermore, new operating regime was created with upstream facilities to maximize degassing upstream and allow higher liquid rates to be processed at Abqaiq. This global optimization allowed over 20% increase in the oil processing throughput, while ensuring a careful balance was maintained to ensure maximal degassing upstream while ensuring no flare taking place. Another area directly impacted was the wastewater treatment area. In order to ensure treated water quality was maintained prior to disposal, residence time was optimized by utilizing alternative storage volume following a detailed risk assessment. The damaged columns were repaired rather than replaced by removal to fabrication shops in order to reduce wastages as well as time for repair. A core value throughout the restoration was embed sustainability, safety, and enhance resilience into the design, and the column repairs were utilized to upgrade metallurgy, install a new feed distributor for increased reactive area utilization, installation of vapor balancing lines for improved thermosiphon stability, as well as enhance entrancing process safety by making the column suitable for vacuum design condition. These enhancements have all yielded a reduction into the facility energy intensity by 0.3%. Gentlemen, a total of 58 design packages were developed, reviewed, and tracked through an optimized MOC process to achieve this rapid restoration, including multiple risk assessments, and this task was carried out by over 20 process engineers working around the clock. The fruit of these endeavors was the restoration of crude oil production of up to 6 million barrels per day in an accelerated but sustainable and gradual manner, defying expectation and providing stability to oil market as well as wider industrial society, which is dependent on the availability of hydrocarbon fuels. The real success story was that this was achieved without any process safety incident, loss of primary containment, fires, or environmental impact. Furthermore, adversity was used as an opportunity to improve facility resilience, performance, and flexibility. In addition to the performance improvements as I shared earlier, we also increased the firewater availability through reuse of other waste streams. And last but not least, an alternative processing configuration was developed to utilize other columns and control valves and repurposing of piping to utilize up to 25% of plant capacity as an automated backup in case of emergencies. This was an unprecedented attack that any processing facility has had to face in recent times, and the quick restoration of oil production and processing is a testament to the commitment, competency, and creativity of process engineers who were at the forefront of tackling the aftermath of this incident. I would just like to finish by saying that this incident really showcased the importance of capable plant process engineers and their role in providing real, sustainable solution when the chips are down, and it really is a prescient time with the world dealing with COVID-19 for all of us to be reminded of that. This was on the ground, frontline process engineering excellence, which made a significant and immediate difference on global scale. This was my presentation, and thank you for listening.
Okay, thank you very much. Once again, we'll have a short break for questions. So if you have a question, please type it into the questions box. While we wait for those, it's a good moment to thank our judges. All of our IChemE Global Awards judges are volunteers, and they worked hard over the last few months reviewing and scoring all of our entries. You can find more about the judging panel on the IChemE Global Awards website. So we have some questions. First one, can plants have a mitigation or barrier against such an attack?
Well, security currently are looking for a mechanism to tackle and detect the drones, but I don't believe that there is like a real solution. At the end of the day, it's your plant. It's the process safety embedded in your plant and the resilience that you have your plant that can be a real solution to the to any non-destructive incident that can impact the facility.
And a related question to that, really, are there other safety measures and safety integrity levels that can be put in place to prevent larger damage in the future?
Well, I might leave that question to my colleague, Haider Bashir.
Basically, it's really thorough implementation of process safety management. One of the key kind of saving features for us was having the right equipment spacing, having buildings at a suitable distance away from the process, having sufficient flexibility between the process to redirect different types of crude in other places. So really, it was really just embedding good process safety management within the DNA of the facility, which really helped save the situation.
Okay, thank you. We are out of time, I'm afraid, so we are going to need to move on. So thank you very much for that presentation. And it's now time to hear from our last finalist. So please welcome once again from Saudi Aramco, Faisal Al Karuni.
Thank you, Matt. Can you hear me and see my screen?
Yes, we can. Thank you.
Okay. Thank you. Okay. So ever since the discovery of oil in Saudi Arabia back in 1938, Saudi Aramco has become the world's leading oil producer. But born of necessity as an energy company in a desert nation, leading the world's production means very little to us without environmental stewardship. Therefore, we have long been pioneers in water conservation. Ladies and gentlemen, today I'm glad to share with you one of Saudi Aramco's latest initiatives to conserve the natural, scarce, and non-renewable resource groundwater. But before we go any further, I would like to ask each one of you a question. Do you know why groundwater is used in our production in the first place? Well, this is because of the oil required specifications prior to exportation or refining. When oil is first extracted, it gets processed at the numerous gas oil separation plants or GOSPs across our country. These GOSPs receive wet crude oil and separate it into three main categories: water, gas, and dry oil. At these GOSPs, we ensure that the dry oil meets two main specifications. The first one concerns the water content in oil, which is also known as basic, sediments, and water. The water content has to be less than 0.2% by volume, and this is achieved by some techniques such as injecting some chemicals. The second required specification, which is the one relevant to our topic today, is the salt content in dry oil, in dry crude. Salt content has to be less than 10 pounds of salt per 1,000 barrels. Oftentimes, this is achieved by washing the crude with groundwater, a process that is known as desalting. To give you a more clear and detailed picture, let me share with you a simplified schematic of the GOSP process. Once oil is extracted, it comes with associated gas, water, and other contaminants such as salt. At our GOSPs, the crude oil is processed and separated as follows. The crude enters to the high pressure production trap, a three-phase separator where oil, gas, and water are separated by gravity. Let's focus on the oil path for now. The oil then flows to the low production trap. This is a two-phase separator where the oil and heavier gases are separated. Then the crude is pumped. Then the crude is pumped to the desalting train. It first goes to the dehydrator, where emulsified water droplets are separated by electrical coalescence generated by the top-mounted transformers shown in green here. At this stage, the oil is dry already, but it passes to the desalter to remove the wash water. Now, where does this wash water comes from? It is a groundwater that's mixed with oil before entering the desalter. This is done in order to dilute the high salinity residual water in oil. The water separated from the vessels is sent to the water oil separator, where the produced water is de-oiled before it's injected back to the reservoir. And here, ladies and gentlemen, is where we identified an improvement opportunity. The idea is to use the produced water instead of groundwater to wash the desalted oil. But can this be done immediately, or there are some challenges? Well, as a matter of fact, the produced water cannot be used immediately because there are some parameters that must be met first. First of all, the total dissolved solids, or TDS, must meet certain specifications, and it's very high in the produced water, making it incapable of washing oil. Also, although the produced water is de-oiled in the wasp, as we have seen, it still contains some fractional amount of oil. This oil is not necessarily processed, and therefore it could affect the quality of our produced oil. Last but not least, the produced water is sour and contains H2S, which adds complication. These challenges prevent us from using the produced water to wash oil. Unfortunately, the technologies we used in the past had some limitations. However, earlier this year, we implemented the vacuum technology, which helped us to overcome these challenges. Let's have a closer look at it. So it's the technology uses vapor compression crystallization water treatment designed to treat the produced water. The vacuum technology, as you can see, takes produced water and treats it. We use this treated water to wash our crude oil instead of groundwater. And by using this approach, we were able to find an effective alternative to groundwater. The challenges that have been highlighted earlier were overcome as the TDS values after using the vacuum technology were acceptable. In addition, the oil presence was no problem as no foaming was observed from the sight glass of the vacuum vessel. Also, the injected chemicals were able to resolve all H2S issues. So again, by using this approach, we find an effective alternative to groundwater to produce high-quality hydrocarbons and save the groundwater for future generations and other sectors such as agriculture. So this is the end of my presentation. Thank you very much for listening, and thanks to the IChemE Award Committee for their support. If you have any questions, I'll be more than happy to answer them.
Right then, thank you. We will pause for a moment and feel free to type your questions in. While we wait for questions, if you've been suitably inspired by what you've seen and heard this afternoon, you might want to start thinking about your own IChemE Award entry next year. Keep an eye on our website for entry information. We typically open for entries at the start of March each year. So we don't appear to have any questions, so we will move on. Thank you very much, Faisal, for our final presentation. And it's time for what we have all been waiting for, to find out the winner of the IChemE 2020 Oil and Gas Award. So let's begin with our highly commended entries, and they are from Hydrox Holdings and Saudi Aramco Expert ARC. Well done to everybody associated with those entries. But now for the winner. Ladies and gentlemen, the winner of the IChemE 2020 Oil and Gas Award, sponsored by the chemical engineer, is Saudi Aramco and its restoration of its critical oil processing facility. So congratulations to everybody associated with that project. We spoke to Mubarak earlier on. If you're still with us, please come back on the line and tell us how it feels to be an IChemE Award winner.
Thank you very much, Matt. This is really fantastic to hear and to receive this award. to have the recognition of our peers for the immense hard work and creativity of the oil plant processing engineers. It is an absolute pleasure for me and to accept this on behalf of the, I guess, all the team, all the processing team here at UpGig. So thank you again. Thank you very much.
Well, congratulations and well done to all of our finalists. Thank you all for giving up your time today to be with us and share your work with us this afternoon. So that is the end of the webinar. Like I said, there are plenty more IChemE Award webinars to come throughout November. So if you've enjoyed this session, do check out our website for the other sessions that are still to come. But for now, it's congratulations to Saudi Aramco and goodbye.